All right, here we go. So today we're going to kind of pick up where we left off yesterday. This is really more about conservation of momentum, but we're going to learn that there are different types of closed system interactions, and we're going to learn how to solve those. All right. So just so that you know, a closed system interaction just means a system where the only forces are internal forces. I guess I should say the only unbalanced forces are internal forces. So a car colliding with another car, or one person pushing another person, or whatever, something like that. All right. And so we are going to learn that there are 4 different types of such interactions. All right. So the first one, there we go. So the first one is what is called a completely inelastic collision. All right. This is a collision in which the objects stick together. All right. When this happens, you actually end up losing energy. And there is no type of collision in which you lose more energy than in a completely inelastic collision, all right? And actually, the example that I did in the last video was one of those, right? Where we had the 2 carts that stuck together, all right? Now, and a collision that is just called inelastic is a collision in which the objects don't stick together, but you still lose some kinetic energy, all right? So honestly, these are, I guess those 2 types of collisions in the real world are probably the most common, I guess. All right. Now, this third one, the one here in green, an elastic collision, really doesn't occur very frequently in the real world. Certainly not on a macroscopic scale like Hertz colliding. All right, because in an elastic collision, the objects don't stick together, and all of your kinetic energy is conserved. All right. Now, like I say, in the real world, this doesn't really happen because anytime 2 objects collide, they produce sound, right? And so energy is lost there. Sometimes your objects get deformed, right? They get bent, or if 2 cars collide, you bend the cars, right? You lose energy there in bending the cars. All right. But for problem-solving purposes, this is definitely a thing you're going to have to know how to do, which is solve collisions that are elastic. All right, and so the big thing to remember about an elastic collision is that all kinetic energy is conserved. So that means that the total amount of kinetic energy you have before the interaction is equal to the total amount of kinetic energy you have after the collision. All right, and finally, sometimes your interaction is what's called an explosion. Some people call this super elastic. All right, and this is an interaction in which the objects actually gain kinetic energy. Okay. So a simple example of that would be, maybe you've got 2 people standing on skateboards pushing each other, right? So the idea is, before they push each other, the total kinetic energy is 0. And then if Roy pushes Sally, Sally pushes Roy, they both roll apart. And so you're now going to have more kinetic energy than you had beforehand, right? So basically, the only way that this would happen is that you gain kinetic energy is if you converted some form of potential energy into kinetic energy, right? So here you're converting the chemical potential energy from Roy's Cocoa Puffs into kinetic energy, okay? A bomb exploding is the same thing, right? You're converting so here's your bomb, right? You're converting the potential energy in your TNT, and here's the little shards of your bomb, right? Going in opposite directions, right? So that's the deal there. All right, so those are the 4 types of collisions. Now, what is important, and this I cannot stress this enough, in fact, so much so that I'm going to add a page. Momentum, I just put momentum. I'm going to leave it. Momentum is, all right, momentum is conserved in any of these interactions. All right, so all 4 of these, your momentum is conserved. And so remember, that means that the total momentum you have before the interaction is equal to the total momentum you have after the interaction. All right? Now, the difference is the energy may or may not be conserved. All right? So let's run through and do a quick example. All right, so let's begin this. There you go. So there's our first example. Take a second, write it down. All right, so here you're given these two objects that collide. And then you need to find the final velocity of the truck and determine what type of collision it is. So this is totally an honors style problem, all right? So let's kind of plow through this real fast, all right? So here's our truck. My board needs to be calibrated. So the mass of the truck is 1,250 kilograms. The velocity of the truck initially is 5 meters a second. It's going to collide head-on with a 750 kilogram car. So here's our car. The mass of the car is 750 kilograms. It is going at 8 meters a second. Velocity of the car initially is 8 meters per second. Notice it's going the other way, so don't forget that negative sign. Immediately after the collision, the car is going backwards, which from our perspective is going to be this way. So the velocity of the car final is 7 meters per second. And we are trying to find the velocity of the truck final. Okay, so there's our setup. All right. So to solve this, it's a collision. So the first thing I know is that because it's a collision, my total momentum will remain conserved. So all I'm going to do is, let's do one of these. I know that the total momentum before the collision is equal to the total momentum after the collision. That means the momentum of the truck before the collision plus the momentum of the car before the collision equals the momentum of the truck after the collision plus the momentum of the car after the collision. That means that the mass of the truck times the velocity of the truck initial plus the mass of the car velocity of the car initial equals the mass of the truck velocity of the truck final plus the mass of the car velocity of the car final, right? And plug in your numbers, right? So I'm going to be sloppy about my units in the interest of time. And so what are we going to get here? You get 1250 times 5 plus 750 times -8 equals 1250 times the velocity of the truck final plus 750 times 7, right? And solve. And you'll discover that the velocity of the truck final, if you do the math on this, comes out to be -4 meters per second. Oh, cool. All right, so that's that. So now the question wants to know what type of collision it is. All right, so let's put this here. All right, so first of all, let's see. They didn't stick together. And the reason I know they didn't stick together is because they don't have the same final velocity. All right, so that means that it is not completely inelastic because they didn't stick together. All right, now I just got to decide what happened to my kinetic energy. Did we lose kinetic energy? Did we conserve kinetic energy? Or did we gain kinetic energy? All right, so that's basically the deal. All right, first of all, decide if they stick together. If so, it's completely inelastic. If not, you have to see what happened to your total kinetic energy. All right, and we went through this calculation at the end of the last video, so I'm actually going to skip that here. All right, but what you would do is you would just say, all right, well, what's the total kinetic energy before the collision? Find a number. In other words, the kinetic energy of the truck before the collision plus the kinetic energy of the car before the collision. That's going to give you a number. And then do the same thing after the collision and compare. All right, and what you'll discover is that during this collision, we lost energy. And as a result, it is inelastic. It is inelastic. Now, super secret ninja trick, check it out. The other thing that I notice here is, remember when you find kinetic energy, it's 1/2 mv squared, right? So it just depends on the speed, not the direction. And I noticed that both of my vehicles slowed down. The truck went from 5 meters a second to 4 meters a second. The car went from 8 meters a second to 7 meters a second. Both cars slowed down, so I know I'm going to lose kinetic energy. Okay? All right, so all of that is stuff that you should have been able to do in honors last year. Nothing new there. This next thing is, however, new. All right? It turns out there is something special about elastic collisions. All right? They have a special property, and that property is as follows. All right, so let's do this. So first of all collisions for simplicity, well, I guess it's not even for simplicity. Let's see, is this going to be, I guess I should say elastic collisions involving two objects. Objects. All right, if you have more than two objects, then it gets a little bit more complicated. All right, so all collisions have the property that the change in momentum for one of your objects is equal but opposite the change in momentum for your other object. All right? In other words, mass times, in other words, the mass of A times VAF minus VAI, right? Mass times change in velocity is equal to the change in momentum for the other object. So negative mass of V times velocity of V final minus velocity of V initial. Right? So that is one equation. Okay? Now, 2. If it's elastic, then that means that the total kinetic energy before the collision is equal to the total kinetic energy after the collision. Notice that's the same as saying that the change in kinetic energy for object A is equal to, but opposite, the change in kinetic energy for object B, right? Okay? In other words, whatever kinetic energy is lost by one must be gained by the other. Okay? So let's see, change in kinetic energy. So the change in kinetic energy for A, so that's 1/2 the mass of A times VAF squared minus 1/2 mass of A times VA initial squared, right? So that's the change in kinetic energy for A is equal to the opposite of 1/2 the mass of B times the velocity of B final squared minus 1/2 mass of B velocity of B initial squared. Ooh. All right, so let's factor some stuff out here. So first of all, the 1/2s go away, right? If I multiply everything by 2, then the 1/2s go away. So let's go ahead and get rid of all the 1/2s. All right, so now what I'm going to do is I'm going to factor out the mass of A. All right, so this becomes, let's see, this is the mass of A times VAF squared minus VAI squared equals negative MB times VBF squared minus VBI squared. All right, and I know, because I took algebra something, that this is a difference of squares, right? Look, VA squared minus VA squared, that's a difference of squares, right? So this is the mass of A times, let's see, difference of squares. So that's VAF minus VAI times VAF plus VAI, right? Equals, oh no, I'm so out of room. All right. Equals, let's do one of these. Haha, look at that, smart board. All right, equals, same thing, I'm going to factor this. So negative MB times VBF minus VBI times VBF plus VBI. All right, we're almost done. So, and furthermore, holy cow, look at this, we're almost done. It's something super cool is going to happen. Look, this is equal to this. This is equal to this. And so they cancel out. I'm going to pause before I cross them out. So this is equal to this. This is equal to this. So divide both sides by this, and they cancel out, which leaves us with this. The velocity of A final plus the velocity of A initial is equal to the velocity of B final plus the velocity of B initial. That is super important. That is true only for elastic collisions. Let's summarize. All collisions have total momentum before the collision equals total momentum after the collision. Elastic collisions, only elastic collisions, have this weird, but I shouldn't say meaningless, this result that if you take the initial velocity and final velocity for each object and add them up, they are equal. Cool. So what this ends up becoming is, for elastic collisions, we now have a system of equations. Two equations, usually two unknowns. 9 times out of 10, those two unknowns are the two final velocities. All right, so let's solve a problem like that, and then I think we're almost done. All right, so here's our example. Example number 2. I'm gonna All right, so let's do an example here. So we got the same setup, same two vehicles colliding under the same circumstances, but this time I've told you that the collision is, in fact, elastic, okay? So here we go. So here's our truck. Ooh, I just changed my pen thickness. All right, so the mass of the truck is 1,250 kilograms. The velocity of the truck initially is 5 meters a second. Over here we got ourselves a car. Mass of the car is 750 kilograms. The velocity of the car initially is negative 8 meters a second. And this time, it says find the final velocity of both vehicles. Notice they don't stick together either, right? Because it's elastic. So that means that they're going to have different final velocities. So I got to find the velocity of the truck final, and I have to find the velocity of the car final. All right? So, like I said, this is going to be a system of equations. All right? So let's see how this works. So first of all, let's buy ourselves a little bit of space here on the board. Okay, so what do we know? So first of all, it is elastic. So that means the velocity of the truck initial plus the velocity of the truck final is equal to the velocity of the car initial plus the velocity of the car final. All right, so notice that each side of this equation doesn't really mean anything, right? It doesn't make sense to add initial and final velocity. But mathematically, it is a good problem-solving tool. All right, so what do we get? We get 5 plus VTF equals negative 8 plus VCF. So let's go ahead and add 8 to both sides to get that VTF plus 13 equals VCF. Okay, so that is equation number 1. Now, equation number 2. Let's go dual screens here. All right, so equation number 2 says that the total momentum before the collision equals the total momentum after the collision. So that means the mass of the truck times the velocity of the truck initial plus the mass of the car times the velocity of the car initial equals the mass of the truck times the velocity of the truck final plus the mass of the car, velocity of the car final. And plug in your numbers. So I'm going to get 1250 times 5 plus 750 times negative 8 equals 1250 times the velocity of the truck final, which I don't know, plus 750 times the velocity of the car final, but I know the velocity of the car final is that right there. So times, oh, I'm totally out of room. Let's scooch all this over to give myself a little more room. Times, let's see, velocity of the car final is VTF plus 13. All right, so now I've got this one big equation where my only unknown is VTF. All right, so if you simplify this mess, here's what you end up getting. You get 6250 minus 6,000 on the left-hand side equals 1250 VTF plus 750 VTF plus 9750. And then I'll let you do the algebra on your own. VTF turns out to be negative, can't read my own writing, 4.75, I think is what that says, meters per second. All right, and then now I can plug that in here and find my VCF, by just adding 13, right? And so that gives you 8.25 meters per second. So that one's going that way, that one's going that way. All right. So that's how those work. All right. You'll have one or two of those on your homework. So make sure you know how to do those. All right. Finally, just a couple special cases, and there's nothing really to do here, but I would just make a note of them and just know that they come up from time to time. I wanted to make this single page. Oh, dang it, I did it again. There we go. All right, so some special collisions, So first, so all of these collisions have the second object being at rest at the beginning, all right? So if you have two objects that have the same mass, all right, and these are elastic collisions where one of your objects starts at rest, okay? So if the two objects have the same mass and one object is moving at velocity v, in order for it to remain elastic, that means that the first object will come to rest and the second object will keep moving at the same velocity the first one had originally. In other words, if this guy's going at 10 meters a second before the collision, then this guy's going at 10 meters a second after the collision. All right, this is two pool balls hitting each other, right? One stops, the other one keeps going. All right. All right, so that is a thing you should know, and that can be solved, proven using the equations I just gave you. All right, next example. If you've got one object that is super huge, colliding with a much smaller object, then that second object, after the collision, will have a velocity that is double the velocity of the really, really large object, okay? I don't know that that one will ever come up, but just, let's see. This one definitely comes up. This one is important, all right? So this is, you got a small object moving into a really big object. So this time, object B is sort of infinitely large, like, say, the Earth, right? So this might be a tennis ball hitting the Earth, all right? And the idea here is when that tennis ball hits the Earth's velocity is not going to change significantly. So to conserve your energy, it has to bounce back at the exact same velocity it had initially. Okay, so if this guy's moving at 10 meters a second before the collision, it's going to bounce back at negative 10 meters a second to ensure that you haven't gained or lost any energy. All right, and I think last one, if you have what is called a glancing collision, where so this guy's going to hit, but it's going to hit kind of at a weird spot, right? So what happens then is it turns out that the two objects, again, so the two masses here are equal, okay? So it turns out then what will happen is the two objects will move off at their own distinct velocities, but those velocities will be perpendicular, okay? So whatever direction object B goes, object A will go in a direction that is at a 90-degree angle to that, okay? Also very useful when playing billiards, all right? And I think that is it. That is it. All right. So these last four things, honestly, like they might turn up as one multiple choice question. I would say that the two that you absolutely need to know are this one, which is one pool ball hitting another pool ball at rest. One stops, the other one keeps going. And then this one where you've got a really little object hitting a really big object. If it's elastic, it bounces back at the same velocity it started with. All right, there you go.